Newton's first law stated that an object would not change velocity unless a net force acted on it, that it would maintain a constant velocity in a straight line, so it wouldn't change direction, it wouldn't speed up, wouldn't slow down unless a net force acted on it. So the converse of that statement would be that if an object did have a net force, it should experience some sort of acceleration. It should experience a change in direction or a change in speed as a result of that push or pull that is unbalanced. So Newton's second law essentially states just that. It's a formula. It says that if a net force acts on an object, you will experience an acceleration. And more importantly, the direction of that acceleration will be the same as the direction of the force applied, or the net force applied. So if I have a net force going to the east on an object, it will experience an acceleration toward the east. And that means it will gain velocity toward the east. If it's going towards the west, I can call that a negative net force, which would produce a negative acceleration, which would produce a negative delta v, and so on. We will use the vector notation ij notation for this. So we can say that a force that might be Fx in the I direction plus Fy in the j direction will be equal to, m is going to stand for mass in this case, measured in kilograms, multiplied by some Ax in the I direction plus Ay in the j direction, with the units that we would normally use for acceleration, which brings us to a big reveal here. What is the units for force? We've been saying that it's the Newton, all right, named after old Isaac himself, but why? Well, the Newton, 1 Newton of measurement, is going to be defined as, I'm going to use the triple lines to represent definition, 1 kilogram, which is our unit of mass, multiplied by 1 meter per second squared of acceleration. So in other words, a Newton equals a kilogram meter per second squared. Now, if we're looking at an acceleration problem and we got meters per second squared, that's already a mouthful. To say that the force is kilogram meters per second squared, it just starts to get a little stumbly. So we could call it a force unit, and that would be easy, except we want to, I guess, throw old Isaac Newton a bone, and so we call it a Newton in his honor. So 1 Newton represents 1 kilogram meter per second squared. You never have to do a lot, well, I shouldn't say never, you rarely have to do a bunch of dimensional analysis and unit analysis to figure stuff out. But it's important to remember where that comes from. It wasn't just come up with out of thin air. It came from this formula. Now, we have seen in our looking at some Pivot Interactives labs, for those of you who are watching who are part of my actual class and doing the Pivot Interactives labs, the connection between force on an object and the acceleration that it experiences. So speaking of the Pivot Interactives, let's go ahead and take a look at it. We had the hanging mass that represents some sort of pull on the system that caused it to accelerate. And if we played the video, the system mass accelerates downward, but not a free fall. And right up into the point where it's going to touch that tabletop, it's pulling on a slider and the whole system is accelerating. And we collected data for if the hanging mass stayed the same, but we changed the system mass to 400 to 500, 600 to 800, what would happen to the acceleration of the system? How would it be affected? Most people said that, well, as the mass, the system increases, you should get less acceleration, which was true. But the exact relationship was a little tricky. And we ended up with a graph that looked like this. And we determined that it was an inverse relationship because as we go ahead and add in the inverse relationship line here, if we include the origin and we start shrinking our graph, we would want to have, as the system mass increased in value, more and more stuff, we should start approaching 0 acceleration. And as the system mass got smaller, we should start approaching a greater acceleration. It should start getting faster and faster. Now, it's going to have a limit of free fall. Can't go faster than that when gravity's pulling on you, but that inverse relationship worked. The question was, how do we linearize it? So that's where I'm going to go to the whiteboard here, where I've got the data points that I just showed you. And we can determine from pivot interactives that we had a relationship like this. The system acceleration was equal to some constant, k, we don't know what it is, or capital A from pivot interactives, multiplied by 1 over the mass of the system. That produced a nice inverse relationship. We had some sort of constant here that the graph would give to us, but we didn't know what the heck it meant. We had some sort of mass quantity that we varied. It got inverted, multiplied by something, and then it gave us a system acceleration. Kind of made sense. But I asked to linearize it. How would we change this relationship in order to make the graph a straight line with a slope we could calculate? So how is this not that? We still have a dependent variable right here, right? We've got some sort of constant here. That's good, we want to keep that. But then we got our independent variable is locked in the denominator, so we don't have a straight line. The question is, how do we make it look more like a linear equation, where we have a y equals m times x? That's a linear relationship. We could add a plus y-intercept, let's not worry about that right now. Well, in this format, our dependent variable, well, that could just represent y. That's no problem. Our slope, our m value, could be whatever the k is. So the last step to try to make this a linear relationship is to say we need a independent variable. I always make that mistake when I'm talking out loud. An independent variable that fits this mold. Well, everything else has kind of like a one-to-one relationship. We need to make a new variable. We need to calculate something from the mass to produce a linear relationship. So our x is going to be equal to 1 over the mass of the system. And if we make that change, we can get a linear relationship. So if we go back to the data, I'm going to go ahead and edit a couple of things here real quick. All right, we're back to where we were. I went ahead and calculated 1 over the system mass. And if I look at that data, it looks pretty linear. I can put in a curve fits, models it, there's a slope value. It's almost the same exact thing that I had as the proportionality constant in my inverse relationship, but now this is going to mean something. Because if this is a linear relationship, I could use the graph to find out what that slope is. The question is, why does that matter? As some people mentioned in class, and I said, how do I make this linear? He said, well, gee, Mr. Zook, why don't you just take this relationship and multiply the ms to the other side? Well, then it's going to look kind of linear. It's not going to be an inverse. You'll have mass of the system times acceleration of the system equals some constant. Well, now that we're looking at good old Newton's second law of motion, this is looking like the formula to calculate it, which means this k, this constant, is some sort of net force on the system. So we know that as there's a greater pull on a system that wants to just be at rest, a big pull on it from the outside, you'll get a big acceleration. And if there's a small pull, you'll get a small acceleration. So this equation we are seeing from laboratory experience, but now we're going to take a look at it from the point of view, just working through it mathematically. So let's say that we have a 75 Newton net force that acts on a 2 kilogram model plane. What will be the plane's acceleration? Well, we're going to solve this problem like we would any mathematical problem. We want to start by identifying variables. And for us, the letter F is going to represent a force. So force could any sort of force, but in this case we are told is a net force, so sigma F is going to represent our net force. And since we're not being told any particular direction here, we don't need to really worry. It's told to us that the net force is 75 newtons. I left the 5 off. And we're told that the mass, which we'll be using the variable lowercase m, is 2 kilograms. And we're being asked to calculate the acceleration rate a. If we were dealing with vectors, we would want to make sure that we include the arrow hats on top of the f and the a. All right, those are vector quantities. Mass is a scalar quantity. There's no direction to mass, it's just mass. But we don't know direction, so we're just going to assume whatever direction this net force is in, that's the direction of the acceleration. That's good enough for us. So let's go ahead and apply this formula that we've got to try to calculate an answer. We should say that the sum of all forces, the net force on an object, is equal to m times a. We want to solve for a, so we can just divide by m. And now we can go ahead and plug in some numbers and see what we get. Now the units here, we know for acceleration are supposed to be meters per second squared. But if we took that unit for newtons that we have and we divided it by the kilograms as we have in our example problem, the kg would cancel out and we'd be left with meters per second squared, which is exactly what it's supposed to be. So that would be our acceleration rate for this model plane. That's a pretty big number. Considering the acceleration due to gravity is 9.8, 37.5 is pretty big. Speaking of which, what about something that's in free fall? Objects in free fall do have an acceleration acting on them, right? So let's say that we have a model plane, and instead of launching it with some net force via a rubber band, whatever it happens to be, what if we instead just dropped it? And we said that the air resistance acting on it was sufficiently negligible. Well, that's kind of weird. Sufficient implies enough, and negligible is nothing. So let's say that the air resistance is negligible on that model plane. It's in free fall. It has an acceleration. What's the net force acting on it? Let's go ahead and calculate that out, because that's going to be important for our next little video. So the net force is our question mark in this case. The mass is 2 kilograms. And the acceleration, let's go ahead and do it as a vector. Negative 9.8 j meters per second squared, which means our force is going to be a vector, so I'm putting little hats on top. They're going out, it's raining, they got to wear their hats. So let's calculate what the net force would be. Now remember, a scalar multiplied to a vector just gets distributed to any term of the vector. It's just a multiplier, that's all it is. It's a scalar multiple. So we can say that that would be 2 kilograms multiplied by negative 9.8 j meters per second squared. So our net force, I apologize, sometimes my sigmas for my net force kind of look like a Z with a bar on top of them. It's not because, I'm trying to promote my own last initial Zook, Z, all that. It's just, I get sloppy. We all get sloppy. That happens. So my net force would be negative 19.6 in the j direction, and then newtons as the unit. So we could put the newtons on the inside of the 19.6, but, or I'm sorry, on the inside of the j, but this is typically how we would write it. So that's the net force acting on the plane as it's in free fall, which means that that's going to give it an acceleration in that downward direction. The question we want to think about next, which leads into another set of notes, is what if the plane is not in free fall? What if it's sitting on a tabletop? It's no longer accelerating, so there's no longer a net force, but if gravity is producing the acceleration and gravity is exerting a force on it while in free fall of 19.6 downward, does that force disappear when the plane's not in free fall? Think about that. We're going to continue in another video with some more notes, but this time we're going to talk about weight, the thing that everybody gets confused with mass, the idea of weight, the force due to gravity. So stay tuned, and we'll check that out in a following video. Sorry, another video.